Let's go ahead and revisit our original maze graph. This time, solving it iteratively using a depth first search stack. I'm going to track the stack over on the right. We start the algorithm by setting our current node as the start node. It's clearly not the end node, so we get a list of its unvisited neighbors. The only neighbor it has is 1. So we go ahead and set that to our current node. We also push it onto the stack. And then we repeat the algorithm. We mark 1 as visited and then select one of its neighbors randomly. The smart decision is to pick 2, so I'm going to go ahead and pick 7 just to show what happens. Our current node is 7, and we push it onto the stack. In the next iteration, we see that our set of unvisited neighbors is empty. So we pop 7 off of the stack, and we set our current node equal to the topmost element in the stack. So we're back at 1. We go ahead and mark 7 as visited as well. The only unvisited neighbor of our current node is 2. So let's go ahead and add that to the stack. We also set it to our current element. Let's go ahead and visit 2 now. The unvisited elements that we can choose from are 3 and 8. Let's go ahead and choose 3. We push that onto the stack and set it as our current element. Next, we mark 3 as visited and then get a list of its neighbors. Its neighbors are 10 or 4. I'm just going to pick 10 so we can see what happens when we make the wrong decision again. So I'm going to set that as our current node and also push it onto the stack. 10 has no unvisited neighbors, so we pop it off the stack and set our current element as the topmost element of the stack, which is 3. We also go ahead and mark 10 as visited. The next element we visit is 4. We set that as our current element and then pop it onto the stack. Why don't you pause the video here and see if you can continue this algorithm. As a brief heuristic, go ahead and choose the highest number node whenever you're trying to make a decision between what node to visit. Go ahead and pause it here and see if you can find the rest of the solution. Okay, so our current node is 4. The unvisited nodes of 4 are 9 and 5. If we choose 9, then we set that as our current node and we push it onto the stack. We see that our current node 9 has no unvisited neighbors, so we pop it off the stack and we set our current element equal to the topmost element in the stack. The next unvisited neighbor of 4 is 5. We go ahead and set that as our current node, and we also push it onto the stack. At this point, we can choose between 11 and 6. I'm once again going to make the wrong decision just to demonstrate how this algorithm runs. We choose 11 and we set it as our current node. We also push it onto the stack. Then we get the list of unvisited neighbors. And since that set is the null set, we pop 11 off the stack and we set our current node equal to the topmost element of the stack. The only unvisited neighbor of 5 is 6. So we set our current node equal to 6, and then we add that onto the stack. Then we can see that the end node is one of the neighbors, and our stack contains a list of elements that we can follow from start to end. We go from the start to 1, and then 2, and then 3, and then 4, and then 5, then 6, and then we're at the end.